Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Our speaker today is a PhD student working with Professor Christina Rotaru, is that right? Ninghui Li. Sorry about that. He anticipates graduating in a year or so. His topic today is using probabilistic generative models for ranking the risk of Android applications. Are you talking about robots today? Or?
Yeah, robots and androids and all that.
All right.
So thank you. It's a pleasure to be here. It's a little bit scary for me because I recognize about half of you from the information security class that I took, so I hope nobody holds a grudge or anything like that about some grade you got or anything. So, like you said, today I'll be talking about this thing, using probabilistic generative models for ranking the risk of Android apps. But first, before I do that, I'm going to just talk a little bit about machine learning, kind of a very high-level overview. Because could you raise your hands if you've taken a machine learning course in the past, or a statistics course, or anything like that? So not too many people. So this will be a very, very high-level overview of some machine learning concepts. So you can ask the question, what is machine learning? And some people have said it's a field of study that gives computers the ability to learn without actually explicitly being programmed to do the things that they do. Or it's the construction and study of systems that can learn from data. So what this really means in practice is that giving some computer or some algorithm a lot of data, can you construct a model for that data and then do something with that? So predict something about the future or extract some meaning from that data that you didn't have just right there in the data, obviously. So one thing that a lot of people do is try to do prediction for future data that you might receive. So if you're given lots of data points, you may want to fit a curve to that data point, to those data points that you're given. So here you can assume that this green line is some function, and you don't know what that function is, but somebody gives you lots of these blue circles that kind of approximate that function. So you know the values at these x positions, and then they add some noise, and so you get kind of an approximation of this function through these blue circles. And so you could ask, like, how would you go about fitting a curve to these blue circles so that when you're given another point, another x value, you can predict what the y or the t value in this case is going to be. So this is kind of the idea of prediction, and so you can think about this as a polynomial curve fitting problem, and if you fit a third order polynomial to this, then you'll get kind of a red line like this, and then, can you see my mouse? Yeah. So if you were to try to predict a value out here, you could kind of approximate that value very closely without knowing a whole lot about the underlying function that generated these data points. You're kind of approximating that function. So this is something you can do, which is prediction. And so you can predict housing prices based on the square foot of a house, or you can do lots of interesting things with this. Another thing that you may want to do is do classification. So kind of the main example in security here is if you have spam email and normal email, and you want to somehow, when a new email comes in, you want to label it as being spam or not spam. You can do lots of different things to do that. A few of those things are the k-nearest neighbors. So if you can, given a new piece of email, if you have a bunch of labeled data of spam and not spam, you can see who the closest neighbors are, and then take kind of the average of your neighbors. And if you're more like spam, you're probably spam, and if you're more like a normal piece of mail, you're probably normal. Or you can do this thing called singular value decomposition. And essentially what you're trying to do there is draw a line through space so that you kind of maximize the partition of this data. So you want all the spam stuff to be over in this red area and all the good stuff to be over in this blue area. And so the learning of that line is one thing that you can do here. And that's, SVD is a little bit more complicated than that, but that's kind of the heart of what you're doing there. So these are all things that I'm trying to introduce at a high level so that later when I'm talking about the paper, you have just a little bit of familiarity with these things because we're using some of these concepts later. So then the next thing I'm going to talk about is what kinds of data can you have. You can have labeled data or you can have unlabeled data. So if you're doing supervised learning, then you'll have lots of labeled data. So you know if an email is spam or if it's not spam. And this is a very effective way to do machine learning, but the problem here is that you need to label this data somehow, and that's not always an easy task. And so on the other side of that coin, you may have unsupervised learning. And here, you basically don't have any labels for the data, and you are trying to find some hidden structure or just fit some model to the data that you can use later for prediction or things like that. And then there's semi-supervised learning, which is kind of a mixture of the two. So you have a lot of data, but you only take the effort to label some small subset of that data, and then you use that to kind of learn. So maybe you only label a few of the messages as spam, and then you can learn a larger structure from that. And then another concept is what are you actually observing, and what's the hidden structure in your data? So you may be able to observe something through the sensors or through characteristics of the email or things like that, but you may not be able to observe everything. And these unobserved things that are there are called latent variables. And so sometimes the main task of machine learning is to actually figure out what these latent variables are and how they relate to your data. One kind of classic example of this is latent Dirichlet allocation, or LDA. And the goal here is you want to find the topics or categories of a collection or a corpus of documents. And so you're given all the words, that's this W here. You're given all the words. And the goal is to figure out what the topics are for this collection of documents. So you may have documents related to business, or documents related to technology, or medicine, or sports, or all these things, and you want to figure out what the categories are and how each document is participating in those categories. And so we have this concept of observed or latent variables. And then why am I talking about all this? Well, all this applies to security. So classification you can use to identify spam or non-spam email, like I had mentioned. You can use some machine learning techniques to try and identify what websites people are visiting. So if you have just a bunch of encrypted data over a network wire that you can sniff, instead of just saying, well, I can't do anything with it, it's encrypted, you can still maybe infer some information there. You can say, well, based on the packet sizes and the timing of those packets, you can still guess, well, it looks like they're going to Google or Yahoo or Bing because of the way that these packets are coming. So you can imagine when you request Google, you request the main page, but then you have to request all the images and the style sheets and all these other things. And so you can sort of build a signature for all these different web pages, and then you can use machine learning to say, well, with some probability, I think they're visiting this web page. You can also use machine learning for anomaly detection. So you can imagine having a process and you're monitoring all the system calls that this process is making, and you can learn some normal behavior that you expect this process to be doing. And then you can, when you see that this process is deviating from that behavior, you can say with some confidence and some probability that this process may be exploited and it's doing something you're not expecting. Same with the network level, you can do the same thing by monitoring all the network points. You can kind of come up with some expectation of your system and then see when anomalies are happening on your system. And because you're dealing with so many points, it's kind of natural to put these into a machine learning context where you can just process this data very effectively. One other thing I'll talk about is, not in this talk today, but just right now, is role mining. So you can imagine that you're given a big access log for lots of how users in a system are accessing different resources or objects on in your whole system. And then you can essentially do role mining to figure out what the access control policies should be that you have in your system to sort of minimize the permissions that are out there and who's doing what. And this is used oftentimes for role-based access control, where you have this concept of roles, and every role has a set of permissions, and then users are assigned to these roles. And so you can kind of come up with the optimal mapping of permissions to roles to users through this thing called role mining. And there's been a lot of research recently in that direction. And there's lots of other things too. So you can do this for pattern recognition. People use this to do facial recognition, which is a big privacy thing. And the list goes on and on. So all that is to say, I think this is an important thing, and if this interests you, then I would encourage you to look into it more. We're collecting more and more data in all of these systems, and corporations, they have these security information and event management systems that they're putting in their networks and on their systems so that they can collect really big logs of all the events that are happening in their corporation. And you have all these mobile sensors and mobile phones that you're getting data from these days, and cloud computing, you can collect a lot of data there. And so I think this is a really big challenge and important questions that can be asked for all this big data. And if you read any blogs like the RSA blog or lots of different blogs, they're all talking about big data, what are we doing with it, how can we most effectively use it in the security context. And you have to kind of have a background in this if you want to ask the right questions and leverage all this information. So if this is something that interests you, I would encourage you guys all to take this machine learning course that's offered here, or if you don't have time for that, you can go on to Stanford. Stanford has some videos on Coursera that are pretty good, just to kind of get a background and primer and see if this is something that interests you. So that's my kind of machine learning plug / introduction. And so now I'm going to actually talk about the topic that I'm here to talk about today, which is using probabilistic generative models for ranking the risk of Android applications. And that's really a mouthful, but it's actually pretty simple when we get down to it. So are there any questions at this point? All right. So how many of you guys have Android devices? Smartphones in general? How many? Okay, so like maybe half the class, maybe a little more. Just curious. So, okay, so kind of the motivation behind this is Android has been growing very, very quickly. As of last September, there were 500 million active devices, 1.3 million new activations every day. Google Play had about almost 700,000 applications in their app store that people can download and put on their phones or mobile devices. And I think the truly astonishing thing about this is that they had 25 billion installations, so all these applications have been installed so many times across all these devices. And the reason for this is that it's really easy to install these things on your phones. They've aggregated these into one location, and it's really simple just to kind of click around a little bit, and you find some app you might like, so you go ahead, and it's only $1, so what the heck, just go ahead and install it. And with just a few clicks, you can get this thing running on your phone and doing whatever it is that it does on your phone. And you can just repeat this process over and over, and all of a sudden you've installed 10 or 15 or 100 different apps on your phone, and what have you actually let onto your phone? You're not really sure. So Android security actually is pretty good though. So they have this thing called sandboxing all the applications. Everything runs in its own context. These applications can't really interfere with each other very much unless they've requested permissions to do so. And so it does a pretty good job of kind of separating out these applications. And to perform riskier actions, all these applications have to request permissions. So if you want to send out SMSs, or if you want to connect to the internet, or you want to do all these things, you have to request these permissions in order to do that. The problem here is that all of these permissions, the user is the person who's making these decisions. So they're relying very heavily on the user to make these decisions. And the permissions are kind of confusing. The way they're described, a typical user isn't necessarily going to understand what they're giving away by granting this permission. And it's also hidden away. You have to click a few times in order to see the permissions before clicking the installation button. When you do click the installation button, you are forced to look at all the permissions very quickly, but in practice, I think a lot of people don't look at those because they've already made the decision to install it. They click the install button once, and then they're presented with the installation with all the permissions, and so they're probably going to not be swayed at that point to change their mind. And you have this all or nothing approach to the permissions. You can't selectively say, well, I don't want this app to look at my contacts or my geolocation, but I will allow it to vibrate the device and connect to the internet. You don't have this choice. You have to say yes to everything or you don't install it. So in practice, what happens is most users are kind of conditioned to ignore these permissions and just accept everything all the time, no matter what the app is. So there's been kind of two primary veins of research here. I know that Professor Enck came last semester and talked about these things a little bit as well. So one of the things that they do is they focus on the operating system. So Dr. Enck had Taint Droid, which is an information flow tracking system that will look at how data is passing through the application. So if your contacts are accessed and then later they try and send out your contacts over the internet, this is going to be detected and Taint Droid will stop that. And then the user has to approve it or not. You have AppFence, which can report fake information, and Apex and SE Android, which are basically all ways of constraining what these applications can do. So you can put more fine-grained policies on how these permissions are used and how the data is used. And then another vein of research is to focus on the applications themselves. So you can take these applications, you can decompile them, you can insert your security hooks directly into the application and then recompile it and then run these recompiled applications on your phone. And then it has to abide by whatever security hooks you've placed on there. It's questionable if this is probably a violation of the terms of services of all these apps, and so it's probably not going to be something that's deployed with any wide acceptance. And so then our approach is kind of going away from the system, away from the apps, and we'd rather focus a little bit more on the user. So we want to quantify the risk of an app via something like a risk score, so that we can communicate that risk to the users in a more intuitive way and help them make better decisions about the apps that they're installing. So we kind of set up these properties of a risk score that we think are desirable, not necessary, but desirable. So apps that are known to be malicious should in general have a higher risk score than apps that are not known to be malicious. The risk scoring function should be something that's simple and easy to understand and can be explained to people, or people can at least be educated about a little bit. And the risk scoring function should be monotonic. So a monotonic function is a function that is only increasing, it never decreases. Once it's increasing, it's only ever increasing. So like this function right here wouldn't dip down and then come back up. It's only ever increasing. So this is a monotonic function. And what we mean there is that if you're removing a permission, it should reduce the risk. And if you're adding permissions, it should increase the risk. We don't want the situation where you're removing a permission and it's actually increasing your risk, because that doesn't really make sense. And so this gives the developers a way of kind of knowing how to reduce the risk of their app. So if they think that their app is too risky, they have a very intuitive way to reduce the risk, which is removing permissions. And we kind of envision this as a relative risk score. So you would sort all of the apps by some measure of risk, and then you can kind of cut that into buckets by thresholds, and then you could present that information to the user in kind of a more natural way for them to consume it, as opposed to having to go look at the permissions. They get this very kind of clear picture of the risk that an app presents. So our approach here is we're going to use these probabilistic generative models to sort of construct this risk scoring function. And so we're going to collect a lot of apps. These unlabeled apps, remember I talked about labeled versus unlabeled data, so we just collect a lot of data, a lot of unlabeled data, and we make some assumptions about how we expect this data to behave, and then we pipe this through our algorithm, and we get some model parameters for this data that we collected. And then we take our model, and we want to do prediction with that model. So we take this model and we take a new app and we take the model and we see how well this new app is going to fit together, and we use that to make a prediction about the app. And the better that it fits, the better that this app fits the model, essentially the less risky we'll think it's going to be, because it sort of conforms to what we expect to see. And the worse that this app fits the model, the more risky it's going to be, because it's kind of something we haven't seen before, and so we don't really know why it looks like that, and we expect that to be a more risky application. So we're going to talk about 4 different generative models here. We're going to talk about this basic Naïve Bayes. We're going to talk about a Naïve Bayes with a more informative prior behind it, a mixture of Naïve Bayes, and a hierarchical mixture of Naïve Bayes. The data that we have is going to just be this very simple representation. We don't decompile anything or do anything fancy. We just look at an application, the category that it's in, and then a permission vector. So the category, there are about 26 categories in the Android data set when we looked at it. And then every permission for these apps, so these XI1s, is going to be a 1 if the ith app is requesting the nth permission, and it's going to be a 0 otherwise. So this is just a very easy way to represent these feature vectors. And these permissions are going to correspond to full network access, read phone state and identity, modify or delete this thing. So yeah. So because we're dealing with this 0 or 1 permission data, we're going to assume that these things have a Bernoulli distribution behind them, and essentially all that means is it's a coin flip. And you're going to have some probability of coming up heads and some other probability of coming up tails. So your probability of being a heads is going to be the probability of x equaling 1, which is equal to theta. And we don't know what this theta is yet, but it's equal to theta. And because there's only 2 values here, the probability that x equals 0 and the probability that x equals 1 has to add up to 1 here. And since we know the probability that x equals 1, we can just reduce this so that the probability that x equals 0 is 1 minus theta. So this makes perfect sense. If you have a 50% chance of getting a heads, you're going to have a 50% chance of getting a tails. If you have a 60% chance of getting a heads, you're going to have a 40% chance of getting a tails. And the way that this is expressed as just a single equation is through this this equation here. And so what this says is if this x is a 1, then this second term is going to be 1 minus x, which is 1 minus 1, and this is going to go to 0. And so this whole term, anything to the 0 power is 1. And so this theta value is going to be what actually comes through this equation. And if this x is a 0, then the opposite is going to hold. So this is going to be 0, and this whole term is going to be 1. And then this value over here is going to be 1 minus theta that comes out of this function. And then for a vector of variables, if you flipped a coin twice, say, then it's really just multiplying these probabilities together. And so if your theta value is 0.5, then all of these things are going to happen equally likely. If your theta value is 0.75, then you think that you're probably going to get a 1 more often, and what this turns into, a vector of 1 and 1 is going to be about 56% of the time, and these other vectors are going to be less often. Is that kind of clear? So this is really the main way that we're going to calculate the probabilities for this most basic case. So our most basic model is going to treat all these permissions as separate and independent Bernoulli random variables. And so it's like flipping lots of different coins, one for each permission, and each one's going to have a different probability of coming up. And so then, in order to calculate the probability of seeing any specific vector, all we have to do is multiply all these individual probabilities together, and then we can say the probability of seeing that vector. And so that's what we do. And just a really simple, small example here. Assume we have only 3 permissions. Then this is the equation from the previous slide. If our theta 1 value is, say, 0.1, our theta 2 value is 0.2, and our theta 3 value is 0.7, then for an app with the permission vector 0, 1, 1, we're going to have the first value is a 0, so we're going to see 1 minus 0.1 come through. So this is going to be 0.9. Our second permission was a 1, so we're going to see the 0.2 value come through. Our third permission was 0.7, so we're going to see that third theta value come through. You multiply all those together, and this is the probability of seeing this permission vector. If you remove that middle permission, then essentially all that's going to happen is you're going to flip that middle term. So instead of 0.2, it's going to be 1 minus 0.2, and this is the probability of seeing this permission vector. And then so forth. So that last term now flips, and this is the probability of seeing this last permission vector. So the reason that I chose this example is, first of all, it's very simple, and I think it gives a good, it's a very clear example of what we're actually doing here. But the second reason is this actually violates that monotonic property that I talked about initially. So when one of these theta values is greater than 0.5, then actually requesting that permission is going to give you a higher probability than not requesting it. So when we remove this last permission, we actually see the probability of that vector going down instead of increasing. And that's one of the properties that we said we wanted. So I just wanted to make that point, and that's why I chose this example. And so the next thing that you should be asking is, well, how do you calculate these theta values? And the way that we do that is using a maximum a posterior estimation to determine the model parameters. And essentially what that means is we want to find the posterior distribution for our data that's going to maximize the probability of our data fitting those model parameters. And to avoid overfitting, we use a beta prior. That's not really important, but it'll come into play in the next model. And so what this means in practice, it's all this fancy language, maximum a posterior estimation. But all this really means is we're going to take the number of times a permission was requested divided by the total number of data points we have, and that's the probability that this permission is requested by any specific app. So as an example, if we have 100,000 data points in our data set and the jth permission is requested 60,000 times, then we're going to have our theta j value being about 0.6. So that's how we create all of our theta values, and then we use that prior thing to calculate the probability of any permission vector. And this is the basic model that we talk about. So the next model is kind of just a slight extension to that previous model. So in the previous model, all the permissions are treated exactly the same. But in practice, that's not necessarily what we should be doing. So certain permissions are going to be more risky than other permissions. And so we introduce this informative prior. So a high-risk permission, like sending SMS or reading your contact list or recording audio, is going to be weighted differently than a normal, like, vibrate your phone permission. So to capture this, we essentially use these BM values and AM values that I kind of glossed over in the previous model. So a high-risk application is going to get 2n as its BM value. Medium is going to get n, and a low risk is going to get 1. And then we're going to calculate our thetas in just a slightly different way. As an example, same example as before, n is 100,000. The permissions are, permission m is requested 60,000 times. So for a low risk application, nothing changes at all. This is exactly the same, about 0.6. For a medium risk application, what we're ending up doing is essentially doubling the denominator. And so this essentially cuts the theta value in half down to 0.3. And in the high-risk permission case, you're tripling the denominator, so you're essentially cutting the theta value by a third. And so what this does is that even if a permission that's high-risk is requested very, very frequently, it's going to penalize this so that we expect to not see it as much, and that's going to penalize applications that do request that permission. So this is kind of the end of these two simple models that I'm going to talk about. So the interesting thing here is that we'll see later during our evaluation, these actually do a pretty good job. Even though they're very basic, you're just taking averages and then multiplying things together, they actually do a very good job of kind of this risk evaluation that we'll do later. And they're very simple to understand. It's very clear how to reduce the risk of any application because you just have to remove permissions as long as your theta values aren't greater than 0.5. And in practice, the only permission that is greater than 0.5 is internet. All the other permissions are naturally less than 0.5 at this point. And since internet is a high-risk permission, it reduces it to below 0.5. And so these are, and for this naive base with the prior, this becomes a monotonic model. So that's it for these models. So now I'm going to move on to a slightly more complicated model. Remember in the beginning I talked about these observed first latent topics, observed first latent variables. So this time we're going to assume that there's some latent structure hidden in our permissions. So each application is a combination of these latent topics, and each topic has its own probability distribution on the permissions. And so this is now represented by this new equation. And so here you can see that the latent topic is going to have its own theta values for all the different permissions. And so you're calculating the vector against each topic's theta values. And then each topic is also going to have some probability of appearing in our data. And so this is just a slight change to our calculation which represents this. So essentially what this gets us is that we can now represent the co-occurrence of permissions. So before, every permission was independent, and this allows us to now model permissions that occur frequently together. So for instance, for photo, so you can imagine a photo-related latent topic, which takes a photo and writes it out to the SD card. And so these permissions are going to appear together very frequently. Or you can imagine an ad network, which is going to want to know your geolocation and retrieve ads off the internet. And so they're going to appear very often together. And so this is a way to model those latent topics. And then it does get a little more complicated to actually calculate these things. So instead of just averaging, over the permissions requested by the number of data points, we have to use something called expectation maximization to derive these latent topics. And what you do to do that is you basically expand this equation up here out a little more, you marginalize out some variables, and then you end up with some new formulas. And all this is an iterative process. So you initialize your variables, you initialize all your theta km values to some random, to some values, and then you're going to calculate this pz equal k given x and theta for all of the k values. So you have to specify some number of k, and then you're going to calculate this probability for all the k values. And the only thing you don't really know here is this theta km value. So you know the xim, and you know everything else. The only thing you don't know is these theta km values. So you use your guess theta km values to first approximate this pz equal k given x and theta. And then you then take that, once you've calculated all of them, you then take all those values and then you plug that into this bottom equation and you do this maximization step. And now you're refining your theta km values given what you had just calculated. And then you just iterate over that. And so now you use the theta km values you had previously calculated to then refine your probability of z equal k given x and theta. And then you just iterate. And you do this until you converge, or you do this for some number of iterations, and then you stop. And then you have your latent topics, and you have your distributions over those latent topics, and then you're happy, presumably. So the main problem here is that you kind of lose this monotonic property in this model, because now some of our theta kms may be greater than 0.5, and it's kind of more difficult to reason about how it's going to affect when you remove a permission or don't remove it. So this is the next model we talk about. So the final model that we're going to talk about is a slight tweak to this. So in the previous model, we assumed all of our data was basically the same, and we learned those latent topics with the same probabilities across all the data. And in this model, instead of assuming that all the data is the same, we're going to incorporate those category labels that we had talked about initially with the data. And then we're going to learn the latent topics, so we're going to learn the theta z values across all the data, but we're going to learn these the probability of z's only across the categories. And so what this allows you to do is, so for the photo and video category, you're going to put a higher preference for those latent topics that are related to photos and things like that. So that photo, take a photo and write to the SD card is going to be highly expressed in the photo and video topic category, and not probably as highly expressed in like the gaming category or things like that. And the math here gets kind of complicated kind of quickly, and so I'm not going to go into this, but if you are curious, we do write out a lot of the formulas in our paper, so I would encourage you to go to the paper. So for our evaluation, we collected 2 data sets from the Google Play Market. We collected one in February 2011 with about 158,000 apps, and we collected one in February a year later in 2012 with about 325,000 apps. And we had a small malware data set with about 600 apps in it from some project called the Malware Genome Project. And they give out malware, Android malware, to research communities. So if this is something that you want to use, you could ask them, or you could ask your advisor to ask them to get that. We did some cleaning on this data. We've removed duplicates. There's a lot of publishers who put 1,000 of the exact same app with very small tweaks to it. So you can imagine a wallpaper app that is requesting the same set of permissions, and one of the apps is for dragons, and one is for princesses, and so they have all these different themed apps that repeat very often. But we didn't want that to kind of influence our model unduly, so we removed the duplicates. And that's pretty much the only cleaning we did. And then just to give you a little bit of a high-level intuition into the data, so you can see between the 2011 and the 2012 data set that there are more applications. So this X value is the number of permissions that each application is requesting, and this Y axis is the percentage of applications that are requesting that many permissions. And so you can see that in the 2012 data set there are more applications that are requesting more permissions. And you can see that the malware is actually much different. It's a little unfair because there's so few malware, but the malware in general is requesting a lot of permissions. There are a few malware that are requesting very few permissions, and this is, I think, generally due to the fact that some malware only needs a little bit of a foothold into the system, and then they're doing some sort of system exploit, and then they're gaining more root privileges from that. So to do our evaluation, remember we said in the beginning we want to evaluate more malicious apps as being high risk because we think malicious apps are high risk. And so to do our evaluation, we compare against Kieran and this other thing called RCP, RPCP, which is rare critical permissions and rare pairs of critical permissions. And that's actually something that we had worked on previously and kind of led up to this work. So this is a lot of the same authors from that paper are on this paper. So we compare our evaluation against these two other works. And we basically generate all the model parameters, and the goal, again, is to identify more malware as high risk. And so you can see from this chart that, so these lines up here are all the models that we present in our paper. These two lines right here are the models from our previous work, and this right here is that Kieran thing. The Kieran thing basically created a series of rules, and if you violate those rules, then you're kind of considered to be risky. And so basically what we did is we ranked all the risk for all the applications we wanted to evaluate, and then we slid a threshold going across, and we counted the number of malware apps that were above that threshold, and we counted the number of non-malware, the market data apps that were above that threshold. And the malware apps are this true positive axis, and the non-malware apps are this false positive rate. And so you can see how well we're doing identifying the malware. And you'd prefer these curves to be very tight up, close to 1 up here. But in some sense, you don't want these curves to be too tight, close to 1, because there are a lot of risky applications in the market data set too. We didn't, clean this. We don't have labels for this data, and we assume that there are a lot of risky applications in the market data. And so we don't want it to be too close to 1 in some sense. And so just zooming in a little bit, you can see that this hierarchical mixture of naive Bayes really does perform very, very well compared to everything else. It should, because it's the most complicated. I think it took, many orders of magnitude longer to compute all the parameters for that model compared to the other ones. And then the other ones that we proposed are all kind of fighting each other to outperform each other, and they're all doing pretty well in general. And then these other ones do okay for part of it, but not okay for other parts of the curve. And another way to view this data is to look at the area under the curve, and so we just plot, this is the area under the curve, so how, basically the area under all these curves. And so you can see again that the most complicated model does perform the best, and these other ones perform okay, but a little bit worse, but pretty good. And so that's encouraging, especially compared to the complexity difference between these two between all these models. The fact that these are performing as well as they are is a little bit encouraging. And so, remember I said there are 3 kind of desired properties in the beginning. We want to evaluate malware as being high risk. We want simplicity so that you can explain this to people, and we want monotonicity so that developers can reduce the risk of their applications. And so they all perform pretty well. These first two models are very simple too, whereas these last two models are a little bit more complicated. And then these first two models also kind of maintain that monotonic property, whereas these last two really don't. And just to highlight that monotonic property, I'm going to show you two graphs and then wrap up. So this is showing we ranked a bunch of applications. We sorted them based on how well they fit the models. And then we kind of cut it into buckets every 1%. And then we looked at how many permissions each application was requesting in these buckets. And so what you see here is the average number of permission requests and then the min and max. That's what the error bars are, is the min and max. And so you can see that as you move to the right, you're getting more risky. And as you move to the right, these applications are requesting more and more permissions in general. So it might be a little bit confusing at first because you see these error bars going between like 3 and 8 or something. But the reason for that is because not all permissions are the same. Some have been requested very infrequently. Some are high-risk permissions. So the way that they actually generate into the risk is going to be different. And so these 3 permissions right here may be very high-risk permissions or very infrequently used permissions. And these 8 up here may be very common permissions. And so that's why you see this kind of fluctuation within each bucket. But I can assure you that if you take an app from one of these buckets and remove permissions, then it's definitely going to move to a less risky posture. And comparing this to the hierarchical mixture of naive Bayes, you just see kind of wild swings here. You see that these 15 permissions over here are rated very, very safe in some sense of the word because they fit the model very well. And so this kind of you lose this monotonic property. It's also not clear how well this translates now into a risk score because you can request 15 permissions, and if they're the right 15 permissions, then you can fit the model very well. And so kind of our evaluation of the summary is that all the probabilistic models perform well, but based on that simplicity and that monotonic property, we think that the naive Bayes with the informative prior is actually the ideal model for this, because it is simple, it's monotonic, and you get that preference for risky permissions. And so just the kind of the last conclusion is, remember, this is not about classification. We're not framing this as we want to identify malware and identify benign stuff. This is framed as we want to just sort of find a way to evaluate the risk of applications. And so we can help users make more informed decisions when they're going to install these applications. And we think that this is one way to do that. There are other features that we can include in our data. We could look at the source code of these applications. We could look at how they behave when they're on the system. And this could help us refine these models. But for now, we only looked at the permissions. And generally, this seems to be a pretty good way. It works pretty well, and it seems to be a pretty good way to summarize and convey this information out to users. So with that, I'll open up to questions if you guys have any.
I was looking at the model that you were specifying with the informative prior. So did you look at permission clusters as such? Some applications will be looking, some applications will require a certain set of permissions, and let us say, for example, you have a picture app, a picture displaying app, not a picture taking app. So it would require, the SD card access. It would require internet access. Let's say you want to back it up or something like that. But if your informative prior was saying that you had access to that kind of information where it said that it requires a camera access as well when it doesn't need to, then automatically the probability of that app being malicious becomes higher. So did you look at these clusters as well of applications?
Well, so that's a little bit tricky because we don't actually know what these apps' functionality is, and so we have to really base this just on the permissions. And so the way that we do this is we're learning the models that are going to fit the data we have as well as possible.
Okay.
If we could build, so for instance, with the informative prior in that basic model, we built some of that knowledge into it. If there's a way to build some of that knowledge into those more complicated models too, then we could definitely do that, but we didn't do that. So.
I just had another question. So the 2n and the n and the 1 that you gave, I do see that it's a numerical approach, but Can you just give a background as to why you chose those values?
Those values?
Yeah.
I don't know exactly why we chose those values. We chose them because they seemed reasonable.
Okay.
I don't think that we didn't, again, because we don't have labels on this data, we couldn't really tweak those values and see what the maximum thing was going to be. So we just kind of chose them because they seem reasonable, and they kind of penalized. They penalized the theta values in a way that seemed good.
I mean, they do give good weights to your data,
Right.
so yeah. Thank you.
Okay, I just had a general question.
Sure.
You had mentioned earlier about sandboxing, and I was wondering if it's possible for one application to piggyback off of another. So for instance, one has access to the camera. Can the other app piggyback off of it
Sure.
and access the data?
Sure. So that's definitely possible. And there's been some people who have pointed this out in previous research, so that you can have colluding applications essentially that then reveal information that you didn't expect either one of them on their own to do. So the answer is yes. The other answer is, so there needs to be a way for them to communicate. If they use an explicit channel to communicate, then maybe you can kind of trace that. So one way to do that is you can use inter-process communication. So you can expose these ports essentially out to other applications, but you have to generate permissions to do that, right? So you have to specify a permission that another app is going to request that permission, and then they can use that. So there are ways that maybe you could add some of this back in to our thing, and then so basically when someone requests a permission to use that port, they'd have to also request all the permissions that other application is requesting. There's covert channels, though. I think there's some research that show that you can use the vibration or the volume, changing the volume to actually pass information between different applications. So there are ways to do that, and we're not going to prevent any of that. There is some value there, though, I think, anyway, because it's a lot harder to convince someone to install several different applications on their system. It's a lot easier to, get lucky and have them install one, but the chance of them installing two kind of rare, weird applications may go down. Maybe, I don't know. So does that answer your question? Okay. So any other questions? All right. So if not, then that's it. Thank you.